Welcome to our first lecture on astronomy. We've just finished talking about Earth science. So what we've gone through so far is we did physics, then we did chemistry, and then based on what we learned in physics and chemistry, we did Earth science, otherwise known as geology, where we applied both physics and chemistry ideas. And now we're going to do astronomy, which once again, astronomy has a lot of physics ideas in it. By the way, in Earth science, we also did have that weather, the 2-day section on weather. So we're going to learn about the solar system in today's lecture. So first, the solar system is called that because it's the system of things that orbit about Sol. The sun has formal names like Helios and Sol, and I'm sure there's others that aren't coming to my mind right now. And so the solar system is the system around Sol. So it consists of the sun, which is by far the majority of the solar system, along with the planets, of which the Earth is one. Moons are objects that orbit planets. Planets are objects that orbit the sun. So I saw something recently on Quora saying, well, do moons orbit the sun? Well, yes, they do. In fact, the sun is a bigger influence on their orbit than the planet they're orbiting. But the closest thing they orbit is the planet, and then that planet and the moon together are orbiting the sun. Then we have asteroids. Asteroids are also orbiting the sun, but they are a different type of object from planets. And likewise, comets orbit the sun, but they're a different type of object from asteroids or planets. So that's the stuff that the solar system is made up of. That plus debris, dust and stuff like that. I should point out comets. When I say comets, I mean things in the Kuiper belt plus things in the Oort cloud, which right now those words are not intended to be meaningful to you, but they're icy objects that we find in two locations in the solar system. So let's start by looking at planets. The planets, we have 4 inner planets. You can see those inner planets right here. And then we have the 4 outer planets. You can see them here. And while this is not to scale, that is, the distances are way out there comparatively, I believe it is to scale on the diameters. And so if you look at this, you have the Earth is the biggest. This is the Earth. It's the biggest of the inner planets, but it's much smaller. It's about 1/4 of the size of the smallest of the outer planets. So the outer planets are big guys. The inner ones, small ones. And so we're going to talk about each one of these planets. One of the things that I do want you to be able to do, if you can't already, is to name the planets in order from the closest to the sun out. So you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And oftentimes we look for something, a memory aid, a mnemonic. And so the mnemonic that I learned is my very earnest mother just served us nachos. Okay, the nachos, one of my students, after Pluto was moved down, demoted from being a planet, we used to have that N was 9. It was 9 pizzas or 9 pies. And they said, well, let's change it to nachos. So that's what I use to memorize it. So you have M with a Y at the end for Mercury, very, V for Venus, earnest, E for Earth, mother, M for Mars. Notice there's 2 M's, so that last letter in my is what tells you which one's Mercury and which one's Mars. Just for Jupiter, served for Saturn, us for Uranus, nachos for Neptune. So let's look at these. First, how did we get here? How did the solar system come? to exist? Now, there are two common answers you're going to get. One common answer is the creationist answer. God spoke and it appeared. Or you have the science answer. Remember, the science answer rules out that God did anything, that everything had to occur naturally, and that's the solar nebula theory. And I am not here to tell you you cannot believe your creationist views. What I am here to say is I want you to understand what the science answer is and where it comes from. So the science answer is based on the belief that there are no miracles, that everything that has occurred naturally. And so processes that we see happening today should have happened in the past, and that's how we came to exist. And we know that there is a lot of gas and dust outside the solar system when we call a cloud of gas and dust a nebula. So this picture shows a nebula. And we are able to observe places where we believe new stars are forming, where we have a nebula and a shock wave comes in and compresses it. So the shock wave is coming like this, and it compresses it, squeezes things closer together. And since the force of gravity is G m1 m2 over r squared, that is, it's stronger when things are closer together. When that shock wave moves things closer together, then gravity starts to take over. It doesn't have enough kinetic energy, that is, the temperature isn't high enough to keep things from clumping. And so the gas starts clumping under the force of gravity because the shock wave hit it and caused things to get closer together. And so as gravity pulls it together, you have, of course, most of the matter gets pulled to the center, and that's what formed the sun. But some of it stuck together in chunks outside, and that's what ended up becoming our planets. So here's a picture to kind of illustrate the process. So you start with this big cloud of gas, roughly spherical. You have compression on it because of the shock wave. And notice this right here. On average, you're going to have a little bit of rotation. What direction? Well, that's random. But on average, you're going to have just a little bit of rotation. And as things collapse, conservation of angular momentum means that if things get closer together, they have to spin faster. I think in class we did examples of a person sitting on a chair with their arms out holding masses and then pulling them in, and they spin faster when they pull them in. Well, that's what we believe then must have happened with the solar system. So this small amount of rotation it started with became a much more pronounced rotation, so they have bigger circles. And just like if you are doing some pottery work and you have a potter's wheel and you spin that potter's wheel, stuff will tend to flatten out because, well, it's because of inertia. You probably think of the word centrifugal force, but that's a fictitious thing. It's really inertia. And so we believe that the solar system flattened out into a disk with the sun at the center, and then we have the planets out here. So that's the solar nebula theory on how things came to be a sun with planets orbiting around it. So this is a non-directed process. This is not a miracle process. This is a process using natural mechanisms. And it's the only real option you have if you don't believe in a God. Now, if you believe in a God, that is another viable way that this could have occurred. Now, non-Christians will listen to this and they'll mock and say, well, that's ridiculous. That's not science. No, God making the universe is not science, but that doesn't mean it's false. It just means it's outside of science. Now we have some words here. The center of the disk was a proto-sun, and then we had planetesimals. Planetesimals, little objects that have collected some mass. And you have actually two processes that go along. First, you have condensation. That is things like a water molecule and another water molecule come together and they stick together. That's condensation. And so condensation would have been the first thing that occurred. And then as you get more mass, the mass becomes large enough that you can have one chunk connect to another chunk, and that's accretion. So accretion is chunk by chunk. Here's a chunk, here's another chunk, and gravity holds them together. Whereas condensation is molecule by molecule, and it's molecular forces holding them together. So our first of the not so clickerish questions: which of the following orbits around the sun? Planets, check, we orbit the sun. Comets, check, they orbit the sun. Asteroids, check, they orbit the sun. Everything in the solar system orbits the sun. So let's look at the sun then. The sun is a star. You look up in the sky and you see, Aldebaran or Venus. Venus is a planet. Or Vega. Those are stars. The sun is a star. I wouldn't say like them because there are variations in stars, but the sun is actually a fairly average star. Why we see the sun differently than we see the other stars is because of distance. The sun it takes light, about 8 minutes to get from the sun to us? Whereas the nearest star other than the sun, it takes light over 4 years to get to us. So you can see the sun is way, way closer. And because it's way, way closer, we see it much differently. And we can do a lot more study and understanding of the sun. So the sun is by far the best understood star because it's the closest star. It's composed of mostly hydrogen in the plasma phase. What that means in the plasma, a plasma is an ionized gas. Well, hydrogen should have a proton with one single electron orbiting it. So if you ionize it, you take away that one electron, and what you're left with is just protons. So when we say hydrogen in the plasma phase, we mean a bunch of protons, proton gas. In the very core of the sun, we have hydrogens that collide with other hydrogens. And in a multi-step process, you have, this is a net reaction. 4 hydrogens come together to produce a helium-4. That's 4 protons give you 2 protons and 2 neutrons bound together. It's complicated. It also gives you some gammas. I think it's 2 gammas. And some neutrinos. And some electrons. I think that's the full net reaction. I didn't look it up. But you have 4 hydrogen gives you this. And there's a lot of energy released in the process. How much energy? Well, 4.5 million tons of mass are converted to energy each second. Now, Einstein said that energy equals mc squared. So c, that's the speed of light. So c squared is 9 times 10 to the 16th meters squared per second squared. And a ton is somewhere in the ballpark. A metric ton is 1,000 kilograms. And so 4.5 billion kilograms per second. Now 4.5 billion kilograms, that's 4.5 times 10 to the 9th kilograms times 9 times 10 to the 16. It's an enormous amount of energy that the sun is releasing every second. But keep in mind, the mass of the sun Let me change color, just too much red here. The mass of the sun, circle with a dot in it is the symbol for the sun, is 2 times 10 to the 30 kilograms. So if it's losing about 4.5 times 10 to the 9th kilograms per second, it's going to take a very long time for it to lose all of its mass. If it were to continue doing this until it had no mass, it would take us 2 times 10 to the 30 kilograms divided by 4.5 times 10 to the 9th kilograms per second. That's equal to, let's see, 2 over 4.5 is 1.11 times 10 to the 20 seconds. Convert that to years, and it's somewhere in the ballpark of, I think it's somewhere around like 10 to the 12 years. A very, very long time before the sun would ever run out of mass by this process. Of course, what it is going to run out of is available hydrogen fuel, right? Because it's the hydrogen fusing into helium. So the sun only has about 5 billion years left of fuel. We believe it's been operational for about 5 billion, has about 5 billion left. And there's actually some science behind how they get that age. It's not a number pulled out of a hat. And notice this, a tiny fraction of this energy reaches the Earth. Why a tiny fraction? Because here's the sun and its energy is going all over the place. And the fraction of the area of a sphere around the sun that's made up by the Earth is really tiny. We're not going to do the calculation, but it's just a very tiny amount of the sun's energy that we receive. And yet that energy is what powers virtually everything we have. So, now the question about this topic, strictly speaking, in every second that passes, what happens to the mass of the sun? Does its mass decrease, remain constant? Does its mass increase? Or does the mass reinvent itself? Well, reinvents itself was there to be a silly answer. And the sun is converting mass into energy. So that means it's losing mass, decreasing mass. The sun is getting lighter. It's on a diet. Okay, that's all we're going to study about the sun today. So now let's talk about the inner planets, Mercury, Venus, Earth, and Mars. We have some interesting rules. Orbital speeds, that's the speed in which the planet is going around the sun, decreases with increasing distance. In fact, we have an equation that says the period, the time it takes to do one orbit in years squared is equal to the orbital radius in astronomical units cubed, where 1 astronomical unit is equal to the average distance between sun and Earth. So if R gets bigger, P gets bigger, that is, it's going to take longer when an object is farther away from the sun, and speed is equal to the distance for one orbit. So circle 2 pi r divided by the time it takes to do an orbit divided by the period. So you can put those together, and that's going to be equal to 2 pi r over r to the 3 halves. Or in other words, equals 2 pi over the square root of r. Now the units there are kind of messed up, but as r gets bigger, the speed is going to decrease. And one of the things we're going to do in lab next week is we're going to look into this, and we're going to look and see what the actual equation is. So now let's look at particulars. Mercury, closest planet to the sun. Because it's close to the sun, it gets a lot more heating from sunlight. And so in the daytime, it's hot. That is very hot. So we would obviously be incinerated if we were on the surface of Mercury. Of course, being incinerated would only be one of our problems because it has almost no atmosphere. Almost no atmosphere. I could have said it has no permanent atmosphere. There is a certain amount of hydrogen that is collected because it's blown there from the sun. The sun is blowing hydrogen off as well as just using up mass. And so that hydrogen may be trapped for a week or two, and then it escapes. It escapes because the temperature on the planet is so hot and its mass is small. Now, I say it's so hot, but at nighttime, yes, you have night on all the planets. Nighttime means that you're on the side of the planet that's not facing the sun. So for any planet, that's going to be half the planet is at night and half the planet is at day. Because it has no atmosphere, you take away that solar heating and it very rapidly cools. So it's extremely cold on places where you don't have sunlight, which means, of course, we would also freeze. So we'd be incinerated and frozen and incinerated and frozen if we were to walk on the face of Mercury. It's only slightly larger than our moon. Just think about that. Our moon is much smaller than the Earth, but it's just slightly smaller than Mercury. One last thing. Mercury has the most eccentric orbit. Now you think about the word eccentric, strange is the common synonym, and it's correct. We have the sun and we have Mercury orbiting around the sun, and Mercury's orbit isn't very close to circular, not nearly as close to circular as all the rest of the orbits. And because it's A, close to the sun, and B, eccentric, it has set up a weird orbital pattern. It has, if you were to have one side of Mercury indicated here with a, like that, as it goes around, in the time that it takes to do one complete orbit, it will have done rotation so that it comes about looking like this. And so it will have looked like it's gone through half a day. I think that's half a day. And then the next orbit is the full day. It has a 2 to 3 orbital resonance. So in 2 orbits, I think it's done 3 complete rotations. But because of the direction it is rotating, I believe that comes out to be only 1 day. So it's very, very odd. The next planet, Venus. Venus is the female planet. By international convention, all but I think it's 2 places that are neutral have female names. So you have things like named after Aphrodite or Sacagawea or things like that. Things on Venus are named after females, people, or goddesses or whatnot. Notwithstanding that they're female, it is a very inhospitable place. Inhospitable because it has a very, very thick, dense atmosphere that's mostly carbon dioxide. So that atmosphere, I notice it says here the diameter is 95% that of Earth. That is, the size is very similar to Earth, but its atmosphere is about 100 times more dense than Earth's, which means the atmospheric pressure is about 100 times bigger, which means we would just be crushed on the surface of Venus. But if the crushing doesn't get you, the acidic nature of the atmosphere would, or the fact that you can't breathe, or the fact that it is diabolically hot there. The temperature on Venus is somewhere around 800 degrees Celsius day and night. Why day and night? Because you have a thick atmosphere that distributes that heat all around the planet. So the planet is pretty much in equilibrium thermally. And you have a runaway greenhouse effect, that is, that the atmosphere allows the visible light through, but it stops the infrared from getting out. So it is just inhospitable. Now, we have, as humans, mostly the Russians, explored Venus. The Russians have landed a number of spacecraft there, their Venera spacecraft. And so there has been some surface exploration, but the spacecraft simply do not last long because of the high temperature and the acid content of the atmosphere and the high pressure. So we have mapping knowledge that comes from satellites orbiting. And I want to point something out. This here is an artifact. It's an artifact of the composite image. To get this image, they have satellites that orbit Venus and are constantly taking pictures. And then they take those pictures and they combine the pictures, matching up the features to get the entire picture. So this is what we call a composite image. If you know somebody who's a flat earther, they probably have learned to parrot things like, oh, all of NASA's pictures are CGI. This is not computer generated graphic image. That's what the I is, image. This is not a computer generated image. Yes, it used a computer to put the photographs together, but it is actual photography. And it's like ignorance is worshipped in the flat earth community, and they will just say any picture that NASA has is just CGI. It's all fake. It's what they want us to believe. It's not based on reality. And you'll even see people, if they have real images, why don't they show them? You can point to the image. No, that's not real. Okay, third planet. Third rock from the sun used to be a TV show. The Earth is the third rock from the sun. Why rock? These inner planets are all rocks. We call them terrestrial because they have Earth surfaces. And the Earth happens to be in what we call the habitable zone, also known as the Goldilocks zone. I'm sure I spelled Goldilocks wrong. If you are much closer than Earth's orbit, it's too hot. And if you're much farther than Mars's orbit, it's too cold. But if you're around where Earth is, it's just right. It's the Goldilocks zone. And it's in this distance where water is neither solid, we'd call that ice, nor gas, we'd call that steam, but liquid. So on Venus, there is no liquid water on the surface because it's too stinking hot. And so you have water in the atmosphere, but it doesn't do you any good. We need liquid water. Mars in theory could have liquid water. We'll talk about that in the next slide. The Earth is our home. We know it very well. All of our geology fundamentally is done here on Earth, and then we take the knowledge we have from geology and we apply it to try to understand other planets. So the last of the inner planets, the last of the terrestrial planets is Mars. Now Mars is only about half the size of the sun, or of the Earth. Sun would be a different object. So it's a much smaller planet than the Earth. And because it's smaller, its atmosphere isn't as strong. It has a very thin atmosphere. Its atmosphere is only about 1% as dense as the Earth's atmosphere. It's 95% carbon dioxide and 0.15% oxygen. So you couldn't breathe it. There was a silly, I think it was Red Planet or something like that, a movie, not the TV show, where this guy is stranded on Mars and he lives in a greenhouse because the greenhouse has plants, and those plants use photosynthesis to convert carbon dioxide in the atmosphere into oxygen. That's all well and good. But if the atmosphere is only 1% as thick as Earth's, even if that photosynthesis produced 100% oxygen in his tent, in his greenhouse tent, that would be not nearly enough oxygen to live on. He would have suffocated. But there's a lot of confusion. The temperatures, notice the cold temperatures on Mars, very cold. You would turn into a crispy little piece of ice in the night. But the daytime temperatures, that's actually really comfortable. 30 degrees Celsius, that's somewhere like 70s. So we would be really happy with the daytime temperatures. We just have to really bundle up for the night if we were on Mars. But then again, we wouldn't be able to breathe. And the air is so thin that even though the temperature that's measuring average kinetic energy is reasonable, they're not hitting us nearly as much. So we'd probably, in reality, still feel cold at that temperature. And Mars is presently a focus of planetary exploration. And I love to talk about the why of this. Back when I was in graduate school, the Vice President of the United States was a man named Dan Quayle. And somebody asked Dan Quayle, why are we spending so much money to explore Mars? And Dan responded, well, if they find water on Mars, then that means there's oxygen, because after all, remember, water is H2O. And if there's oxygen, that means that we can breathe. Sorry, Dan, there's a breakdown there. Just because there's oxygen doesn't mean we can breathe. I can't breathe underwater, for instance. There's plenty of oxygen there, but I can't breathe it. The problem is Dan was a politician, not a scientist. The scientists were looking for water because water is one of the basic constituents that we believe is necessary for life to exist. You have to have water, you have to have an energy source, you have to have a certain number of elements. I think it's like only 7 elements that are considered fundamental for life. But water is one of them. And so what they're looking for is water, because if they can find water there, then they can say, okay, it is possible that there could have been life at some point on Mars. If they can't find evidence of water, then you cannot say that it's possible there would have been life on Mars in the past. And indeed, they have found evidence that there used to be liquid water on the surface of Mars. What happened to it? Mars, with its smaller mass, doesn't have enough gravitational force to hold on to the water, and anything that was liquid has gone to gas and escaped. So here's some pictures of the surface terrain of Mars. Now, objects in the distance are farther than they appear. And when I say they're farther than they appear, I'm not kidding. Because Mars has a very, very thin atmosphere, you can see for very long distances. So we're talking hundreds of miles you can see, and it doesn't look like they're that far away. And so our explorers, we've had Pathfinder, Spirit, Opportunity, they have done all kinds of exploration on Mars, and they have, in fact, found evidence that Mars used to have liquid water, and they believe there still is ice, frozen water, buried under the surface in Mars. Now, there's a big break between the inner planets and the outer planets. In between the inner planets and the outer planets, we have inner. Then we have the asteroid belt. And then we have the outer. And the outer are so much different than the inner. The inner planets are all rocks. They all have a solid rocky surface. They all have densities that are on the order of 3 to 5 grams per centimeter cubed. The outer planets have densities that are on the order of 1 gram per centimeter cubed. Saturn's is actually less than 1. 1 is the density of water on Earth. And they're all gassy. They're gassy planets. Doesn't mean they have flatulence. It means that they have gas exteriors. So they're gaseous, low-density worlds. They are way larger than Earth. Even the smallest of them is 4 times bigger than Earth, which is the largest of the terrestrial planets. And they're spaced much farther apart from each other than the inner planets are. And so we have the order here: Jupiter, Saturn, Uranus, and Neptune. So looking at them, once again, staying with the order, Jupiter is 11 times Earth's diameter. It is so large. If it was, I think it's 81 times more massive, it would be a star. So it's nearing the limit for what it takes to be a star compared to a planet. So its outer atmosphere is gas. But as you come in, that gas gets thicker and thicker and thicker until at some point you would say, my goodness, this is a liquid, not a gas. But never once would you have splashed. There's no physical change going from liquid to gas. It's a continuous change. And you get down low enough and you have liquid hydrogen, liquid metallic hydrogen. It's like mercury. Mercury is a liquid metal. You have liquid metallic hydrogen that's swirling around. And then underneath all of that, you have a solid rock core. So it still has a solid rock core. In fact, that rock core is bigger than the Earth, but it has all of this gas. Now, I put in quotes here atmospheric pressure. Why atmospheric pressure in quotes? Because where do you find the pressure? Where does the Earth's atmosphere end? When we talked about the atmosphere, we went up there to the exo atmosphere, and the exosphere is what it was called. And so if you come into Jupiter, if you're far enough away, the pressure is virtually zero, and you get down closer and closer and gets bigger and bigger. So what we do here when we say the atmospheric pressure is more than 1 million times that of the Earth's, we define at the, quote, photosphere. The photosphere is where we see light coming from that we identify as, that's Jupiter. There is no physical surface there, but where we see what looks like the surface of Jupiter, that's what we define as the surface. So the atmospheric pressure there, really, really strong. Here's a picture of Jupiter. Jupiter has odd weather patterns. These things here are called belts. And these things here are called zones. So it has belt zone circulation patterns. These are essentially windstorms that go all the way around the planet. Now this here, the great red spot, that is a big cyclonic storm. That's basically a cyclone that has been going on Jupiter since the time of Galileo Galilei. It has, you imagine that's a long, long time for a single storm to continue. And you have other cyclonic storms that tend to occur on the boundary between a belt and a zone. Belts and zones are, like I said, windstorms. And actually, I named these backward. I named the zones and the belts backward. This is a zone. This is a belt. The belts are dark, and those are lower elevation and colder. The zones are bright, and they're higher elevation and warmer. So it has an interesting weather pattern. Also, what you can see in this picture, that's a moon. And that's another moon. We have moons around planets besides the Earth. Jupiter has 4 major moons. And I don't remember the exact number. It goes up all the time as they find new ones, but I'm going to say over 60 minor moons. Minor moons are small little fellas. Major moons are big ones. So its atmosphere, about 82% hydrogen, 17% helium, 1% methane. Obviously, we can't breathe this and survive. It has no definite surface because it's just gas that gets thicker and thicker. But it does have that solid core. Just like Earth's, we believe it's primarily iron and nickel, and it's bigger than the entire Earth. So we tend to think of these gas giants as just being gas, but no, they're gas, then liquid, and then a solid that's bigger than the Earth. Because of its heavy atmosphere, temperatures are uniform throughout. Here's its 4 major moons. Io, you look at Io, this is volcanic. You look at Europa, Actually, Europa and all of the rest of them are icy. Each one is interesting in its own right. Io is volcanic because it's so close to the planet that the gravitational force distorts it, and as Europa comes around, Europa will stretch it. And so the gravitational forces, the tidal forces, they cause high tides because of the moons on Earth, around the moon going around Earth. Well, the moons of Jupiter cause tidal forces that are enough to stretch and work Io. So the planet itself is being stretched and deformed, and that stretching and deforming then causes it to melt and causes all of the volcanoes. So you can see all kinds of volcanic things on the surface there. Now, Europa, I have another slide about that, so let's go on to Europa. Europa is considered a prime location for extraterrestrial life. Why prime? Well, it has an ice covering, has an ice surface. The ice has cracks and stuff that indicates recent deformation. In fact, we have essentially plate tectonics, but happening in ice for Europa. So we have this, and underneath there is a liquid water, and it has volcanoes down there. So you have water, you have an energy source, and scientists think if you have that water and the energy source, you probably have the other chemicals necessary, and that would be a prime place for life to form. And so scientists think that if they're going to find extraterrestrial life, this is a really good prospect. So when scientists have sent orbiters to come and orbit around Jupiter, they're very careful, with the exception of they're very careful to make sure that nothing interferes with Europa. They don't want any spacecraft crashing into it, any debris hitting Europa, because they hope at some point that they can come to Europa with a spacecraft and look for signs of bacterial life. And they don't want a spacecraft to have left debris there with some bacteria on it that could have seeded life, so it would be Earth life that moved to Europa. They want to look for life that started on Europa. Now, of course, you have to know that I have a predisposed belief that God created all life, and so they're not going to find life there. But doesn't mean that people who don't believe in God are going to not look for it. The other two out here, Ganymede and Callisto, these are very large, and the farther away they get, the less flexing they have. Callisto has a very hard ice surface, no plate action at all. Ganymede, you can see that it has places where it's had impacts that have caused major flooding. So it's had its surface broken and then reflooded and reformed. So this stuff here, we call it a sea, or mare in Latin, where it's been flooded and resurfaced. Whereas the surface of Callisto is very old. It has lots of little craters from impacts, but it hasn't resurfaced. It hasn't broken through, had water flood over it to make a new surface. Okay, moving on to Saturn. Saturn is famous for its ring system. So Saturn has rings around it, and these rings are ice rings. Now, you might think Saturn is the only planet with rings, but you would be wrong. All outer planets have rings. Which brings up all the jokes about Uranus. But let's be clear. We don't see the rings around Jupiter or around Neptune or around Uranus. We only see rings around Saturn. The reason is that these are ice rings. These ice rings are reasonably thick, they're reasonably young, and we can see them when light hits them. The rings around Jupiter are very thin dirt rings. So those dirt rings can only really be seen when you have Jupiter between a light source and you. We call this an occultation, and then they can be seen. And so the question comes, where do these rings come about? Now, I've talked about evolution and creation quite a bit here, and you may have heard creationists say, look at the rings around Saturn. Those indicate that Saturn is young. Scientist says, no, those indicate that the ring material is young. The scientific belief is that Saturn, with its very strong gravity because of its very large mass, at some point a comet veered too close. And the tidal forces, that is the fact that the force on something close is stronger than the force on something far, if something comes closer than the Roche limit, the tidal forces will tear it apart. They will shred it. And so they believe that a comet came too close to Saturn and was shredded by Saturn's tidal forces, and then that comet went into orbit around Saturn, creating the rings. And of course, you might say, have we ever seen anything like that? Well, yes, we have. The comet Schumacher-Levy, a few years back now, it's probably been 2 decades now, came close enough to Jupiter that Jupiter's gravity shredded it. Now, most of Schumacher-Levy went into Jupiter, so we don't have rings from Schumacher-Levy, but we have things being shredded. Has to come with the right orbital parameter to set up an orbit around it. So Saturn, over time, it's going to lose its rings. Sometimes Saturn won't have these visible rings in the future. At the same time, Jupiter, it could have a comet come too close and shred it up and form new icy rings. Wouldn't that be exciting? And if it happened, I mean, we would see it happen in real time, and it would actually be very obvious here from Earth. Saturn has a couple of other unique things. Saturn is the lowest density of all the planets. It's less dense than water. It is the least spherically shaped planet. Gravity pulls things into a spherical shape. But because of the amount of mass out here in its ring, it actually is distended in the direction of the ring. So we say it's the most oblate of the planets. And while Jupiter was about 11 times the diameter of Earth, Saturn's about 10 times, not counting the rings. And it's twice as far from the Earth as Jupiter. So Jupiter's way out there, and Saturn's double the distance. We talked about that. I should mention, rocks that make up the rings orbit independently of other rocks, and these gaps are caused by moons. You have 2 actual situations. You have orbital resonances, and you have moons that pull material into it. Saturn has 1 large moon and, once again, over 60 small minor moons. The 1 large moon is Titan, like the Titans in mythology. And Titan has actually been visited by the Cassini spacecraft. It's extremely cold, and its surface doesn't look all of that bizarre. That's all we're going to see about Titan. Uranus, 98-degree tilt is the first thing that jumps out to me. So the sun is out here, and its orbital axis is 8 degrees off of having its pole pointing toward the sun. Now, what this means is, in this picture, you would have basically 1/2 of the planet is in summer, and 1/2 of the planet is in winter. So that's a long, hot summer or a long, cold winter. But as it orbits, eventually you'll get to where the sun is coming straight out of the screen from you. In that case, the whole planet is going to be at essentially the spring equinox. And then it'll keep on going, and this side here is winter, it'll swap which side is winter. It takes 84 years to orbit the sun. We call that the period. And so basically, this hemisphere is going to have summer, That is, this point right here at the pole is going to have continuous sunlight for 42 years, and then it's going to have no sunlight for 42 years. That's pretty crazy. So it's got some really weird temperatures. It also has a number of other weird things. Notice it says a faint ring system, a methane in the atmosphere that gives it its bluish color. Very, very cold. Its diameter is about 4 times that of Earth, and its rock core in the center is about 20% of the planet. So its rock core is just about the same size as the Earth. And notice it's once again twice as far from the Earth as Saturn is. So our spacing is getting much bigger. Now, I'm going to stop right here and mention something important. Uranus it was noticed when they studied its orbit that its orbit didn't quite fit what they expected based on the planets and sun known. Uranus was the last of the naked eye discovered planets. It was discovered by William Herschel. He initially wanted to call it Georgius Sidereus, that is King George's star, but that was not allowed because King George was not a god, and the planets are named after gods. And so it was given the name Uranus, who is the god of the sky. Based on the oddities of its orbit, scientists examined the orbit and they predicted there must be another object that's orbiting beyond Uranus that is causing these perturbations. And so they predicted where it should be and what its mass should be. And then they trained their telescopes there. And lo and behold, they found Neptune, named after the sea god. Notice Neptune is a little deeper blue than Uranus because it has a slightly different amount of methane in the atmosphere. And it's about 4 times the size of Earth, so it's slightly smaller than Uranus. And once again, mostly hydrogen, helium atmosphere with some methane to give it its color. Here they've actually drawn in some rings because it has rings. Neptune's orbit is an elongated elliptical path as well. And remember, Mercury was the most elliptical. Next is Neptune. And so studying Neptune's orbit, they once again said this has some perturbations. There must be another object. They were feeling a little gutsy now. They'd already predicted Neptune and found it. So they predicted that there would be another object, and they predicted its mass and its location. And they went looking, and they found an object that they named Pluto. But it turned out Pluto was not the planet they were looking for. Pluto didn't have anywhere close to the mass necessary. So scientists knew pretty quickly after Pluto was identified as a planet that it really wasn't. But history. So they called Pluto a planet until 2006 when they said, this is ridiculous. Pluto doesn't behave like a planet. Planets come in 2 categories: the rocky planets, which are big rocks, and the gaseous planets, which are big rocks with a lot of gas around them. Pluto is neither of that. Pluto is essentially an ice ball. It's got some ice and some rock, has a density that's midway between those of the planets. And Pluto is not a very large object. It is, in fact, not the largest object that is not a planet. Eris is a bigger object that is just like Pluto. And so Pluto really doesn't have any standing to be considered a planet. Let's talk about what a planet is. Planet is a Greek word for wanderer. Wanderer. The planets, gotta fix that. The planets were objects that were seen to wander through the sky. And, it's kind of Uranus and Neptune, you can't see them. I said naked eye. Actually, Uranus was discovered with a telescope. So Uranus and Neptune, not naked eye, but they're same type of objects as Jupiter and Saturn. So you can see, considering them planets. But putting a whole new type of object that's not a naked eye object in, that would be Pluto and Eris and Quaoar and Haumake. It's Makemake and Haume. Those guys and ladies, they're just not like the other planets. So a new subgroup has been made calling them minor planets or dwarf planets. Actually, dwarf planet is the right one. Minor planets are asteroids. But let's look at Pluto anyway. So it's called the dwarf planet now. They made up that category, so people who are fans of Pluto, the planet, can still say, hey, look, it's a planet. It's a kind of planet. It's just not a planet. It's very different composition. Like I said, it's an ice ball with a rock. It's small compared to all of the planets. Its orbit is very eccentric, and all of the planets, Mercury is a little bit off, but all of the other ones fall very close to a flat plane around the sun. And Pluto's like this. It spends most of its orbital time well beyond Neptune in what we call the Kuiper Belt, and it looks just like its other Kuiper Belt objects. Enough on planets. Let's talk about moons and end this lecture. So the Earth's moon. The Earth's moon, we've studied it quite a bit. Humans have been there. It's about 1/4 the diameter of the Earth. Very similar in size, as we said, to Mercury. Because it's small, it has no atmosphere. With no atmosphere, you don't have any winds to cause erosion. And of course, it has no liquid water. So it basically has nothing to move the surface around and remake the surface. But it does suffer from micro asteroid collisions. Little asteroids are hitting it all the time, peppering it, and it's like it's being sandblasted. When those hit the Earth's atmosphere, we say, ooh, look at the shooting star. A shooting star is usually something that's like the size of a grain of sand, comes into the Earth's atmosphere, it gets ionized, and as it passes through the atmosphere, it excites electrons in the gases that it passes by. They de-excite and give off light, and that's what we see as a shooting star or a meteor. Well, there's no atmosphere on the moon, so they just come and they hit the surface of the moon, and they sandblast it. They break up a little bit at a time. So the surface of the moon has all of this powder because of all of those little abrasions that have occurred. So if you look at this picture, you can see how they leave their tread prints there, and that's like a few feet thick, that powder. Now, I want to point out, a lot of people have analyzed these pictures, and they say, fake. They say, look, the flag is waving. NASA has a really good explanation. This is it's a telescoping pole. And number two, this is a previously folded flag. And so you have creases from the folds that make it so it has that kind of shaded, wavy look. And because you have this telescoping pole and you have no atmosphere to damp it, it will sit here and vibrate for hours before it stops vibrating. So it was moving just a little bit and had those creases, and people said, oh, look at it, flapping in the breeze. And of course, there's no breeze there because there's no atmosphere. And so then they say, aha, see, fake, 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 fake. Well, I do not believe at all that this is fake. I believe these are real pictures of real astronauts really on the surface of the moon. Other people will analyze the shadows, the direction of the shadow, and say those two lines aren't parallel. And there's a lot of arguments people make. And bottom line, yes, no, they really were there. 12 people have stood on the moon. This is Buzz Aldrin in this picture. So how did the moon come to be? Once again, just focusing on the scientific answer. The scientific answer, there's a lot of different hypotheses that have been explored. Like, for instance, maybe the Earth and the moon formed together as one, at the same time as two objects from the same cloud. But they are not similar enough for that to be true. Maybe the moon was something that formed separately and came and was captured. They're not different enough for that to be true. And the ultimate conclusion, the one that fits with the best of our data, is that there was a planetesimal that came and smashed into the Earth. And we're talking something that's large, something that's like the size of Mercury hit the Earth. And so it causes, imagine if you were on Earth then, of course you would die. it would cause basically the entire surface of the Earth to melt, and it would blow a huge amount of the Earth's surface up into orbit around the Earth. And so you have all of this debris orbiting the Earth. So this picture here is the second picture with all the debris orbiting the Earth. And see, the Earth is molten now because of all of the energy of that impact that's heated it up. But then over time, that debris starts collecting because of gravity into an object that we now believe to be our moon. And the reason this matches up with reality is because the composition of the moon is very similar to the composition of the mantle of the Earth. Not the entire Earth, but the mantle of the Earth. And so they say, okay, that makes sense then. It's not just like the Earth, but it's like the mantle of the Earth, because you had the mantle of the Earth had a big chunk of it that was blown off into the sky. I will talk about the moon's phases and whatnot in our next lecture. Have a great day.